November 2018, paper 6, variant 3. In question 1, the student is determining the density of a model in clay. He measures the length L, W, the width, and the height H. Can we measure them using our rulers? Yes, we can do that. The length measuring using the ruler would be around 6 centimeters. If your reading is slightly less than 6, it's okay due to the printing of the pages. Okay, printing sometimes shrinks the actual measurements. The width should be 3 centimeters. If you're less than 3 centimeters, again, it's okay. He has already written down centimeters, so you do not need to write it down again. 6.0 if you'd like, 3.0, and the height would be 4.0 as well. Okay. Can I find the volume by multiplying the length by the width by the height? Yes. 6 times 3 times 4 is 72 centimeters cubed. Suggest a possible source of inaccuracy in measuring the dimensions of the block and describe an improvement to the procedure that will produce more reliable measurements of the block. One possible What could one possible problem be? One possible problem could be in measuring the actual dimensions. Okay, actually taking the measurements. This isn't a regular shape, is it? It's not a regular shape. So there is a difficulty in measuring the actual dimensions. Okay, it's quite difficult to measure the dimensions. One improvement to this would be to repeat, okay, and take average. Repeat and take average. And C, you have a force meter with the model in clay. Record the weight. Can I find the weight from this force meter? Yes, the weight is 1.4 newtons. 1.4 newtons. Can I find the value of the density, rho 1? Yes, I can. W times K divided by V1, in which K was 100. So W was 1.4 times K 100 divided by the V1, which was 72. So rho 1 would be 1.9 or 1.94. Can I include the unit? Yes, you can include the unit. What is the unit? This is the density, so it's grams per centimeters cubed. The V1, the volume was in centimeters cubed. G or the K was 100 grams per newtons. So the newtons was cancelled out with the newtons of the weight, and what you have left is the grams. 1.9 or 1.94 grams per centimeters cubed. The student pours some water into a measuring cylinder and he records V2. Can I find V2? Yes. V2 is exactly 160 centimeters cubed. Describe how a measuring cylinder is read to obtain a accurate value. You may draw a diagram to help you. If you want to draw, you can draw. How can you take an accurate value from the measuring cylinder? Taking the reading perpendicularly to avoid the parallax error. Okay, take the reading perpendicularly to avoid the parallax, okay, error. Record the new reading V3 of the measuring cylinder with the block with the modern clay inside. What is the new reading? The new reading would be 200 and 230. Calculate another value for density 2. Can I find rho 2? Yes, you have rho 2. What is W? W was the previous reading, which was, yes, 1.4. So again, you have 1.4 times 100. 1.4 times 100 divided by V3 minus V2. What was V3? 230 minus V2, which is 160. 1.4 times 100. Okay, this would give you a density of 2 or 2.0 grams per centimeter cubed. Suggest which density 1 or density 2 is more likely to be accurate. Is density 1 or density 2 more accurate? And justify your answer by referencing or referring to the procedure. In my point of view, row 2 is more accurate. Okay, density 2 is more accurate. Why is density 2 more accurate? Because the volume of the measuring cylinder is much better. Okay, volume is taken directly from the measuring cylinder. Measuring cylinder. Actually, someone else could argue that row 1 would be more accurate because the measuring cylinder doesn't give very accurate readings, which is a valid argument. In this case, he would say row 1 is more accurate. So it's okay. Both answers might be correct. Question 2. Students are determining the resistance per unit length of wire X. So you have wire X and you want to find the resistance. On figure 2.1, draw the symbol for a voltmeter connected to measure the potential difference across wire X. Can I draw the voltmeter? Yes, the voltmeter would be in parallel, okay, with wire X. A student adjusts the position of the crocodile clip until the current is 0.8 amperes. In table 2.1, record the value V. What is the value V of the voltage? Yes, it is 1.9. In the table, we need to write down 1.9 or 1.90 to have three significant figures. The student records the potential difference, plot a graph VV on the y-axis. So you have V slash V on the y-axis, and then you have I slash A on the x-axis. You do not need to start from zero, which is quite obvious in this question. The voltage axis, you can start with, let's try 0.8. Okay, let's try 0.8, and then 1.0, 1.2, 1.4, 0.6, 0.8, and then 2.0. Yes, 2.0. This would be a really good scale for the y-axis. What about the x-axis? The x-axis could be plotted 0.4, 5, 6, 7, and 8. For the x-axis, you can start with 0.4, 0.5, 0.6, 0.7, and 0.8. If you want, you can start with 0.3 and end up with 0.8. Can I plot the points? Yes, I can plot the points. 0.4 with 0.81. So 0.4 and 0.81, if I zoom in a bit, would be exactly at this point. Actually, almost at the start of the graph. And then the second point, 0.5 and 1.03. 0.5 and 1.03, so it's right over here. This is the second point. 0.6 and 1.34. 0.6 and 1.34. This is 34. 0.7 and 1.58. 0.7, 1.58. This is the point. And last but not least, 0.8 and 1.9, which is at this point exactly. We need to draw a straight line. So zooming out. Okay. Drawing a straight line using, okay, so points would be somewhat like this. Okay. This is an acceptable line. Why? Because you have 1 point or almost 2 points above and 2 points below, which is okay. This is the best fit line. For the next question, he wants to find the gradient. Can I find the gradient? Yes, the gradient would be using the triangle method. You have to use the triangle method. You have to use the triangle method. So I have to draw on the graph, okay, taking 2 points from the line, taking 2 points from the line. If you want to take the 2 points from the table, it's okay. If you want to take them from the line, it's okay again. Okay, if I take the 2 points from the table, they would be 1.9. Okay, 1.9 minus 0.81 divided by 0.8 minus 0.4. Can I find the slope? Yes. 0.9 minus 0.81 divided by 0.4. This is 2.7. Okay, 2.7. I'll just remove this line, but again, you should have it drawn on your graph. So my graph or my gradient would be around 2.7. If your gradient is plus or minus 0.1 or 0.2, it could be okay. Figure 2.1 shows the wire X, measure the length L. Can I measure length L? Yes, it would be 4.5 centimeters. Again, if your reading is slightly less than 4.5, it is okay. The wire is 1/3 the scale. What do I mean by 1/3 the scale? Can I find the actual length? Yes, I can find the actual length. I need to multiply by 3. You need to multiply by 3, which is 13.5 centimeters, or whatever your reading is, times 3. And then, can I find the resistance? G times K over L. Yes, G, the gradient, which I found, which was 2.7. 2.7 times K, which is 1. K is just 1. But 1 just to remove the centimeters. So you need the resistance to be in ohms. You need the resistance to be in ohms. And then the length, the capital L, which is 13.5. What is 2.7 divided by 13.5? This is 0.2. Okay? 0.2 or 0.20 ohms if you'd like. Okay? If your resistance is 0.21 or 0.19, this might be acceptable as well. A student notices that the resistance wire becomes very hot when the crocodile clip is connected to the short lengths of the wire. Suggest an improvement. If you want to decrease the temperature, then you can use a smaller resistance. Okay? I'm sorry, a smaller current, I mean. You can decrease the current. You have actually two precautions. You can either decrease the current or switch off the circuit, circuit between each reading. Okay, between each reading. Okay, question 3. We have a ray trace sheet. Measure and record in table 3.1 the angle alpha. Can I find angle alpha using my protractor? Yes. Angle alpha. Okay, you need to place the protractor this way. Okay, the center of the protractor should be here, and then place the protractor this way. You'd find that this angle would be 20 degrees. Okay, 20 degrees. So angle alpha is 20 degrees. Now, draw a normal L. Let me remove this. Draw a normal L to point AB. Okay, to the line AB at point N towards the top of the page. Label the top L. Okay, so you need to draw a normal at this point all the way to the top using definitely a ruler, and you should name it L so that the normal line NL. This is your normal line. And then 2 points or 2 pins P1 and P2 are placed on line LN a suitable distance apart. On figure 3.1, label suitable distances for P1 and P2. You have to place the points as far as possible from each other. So, for example, this is P1 and this is P2. The distance between them has to be at least 5 centimeters, which we already know. The distance between these two pins has to be at least what? At least 5 centimeters. Soon places the reflecting surface on line CD, and he repeats the experiment. Draw a line passing through P3 and P4 reaching point N. P3 and P4 reaching point N. So you have to join these two lines, okay, reaching point N. Again, using a ruler to be very accurate, from 3 to 4 all the way to N. Okay, and measure the angle theta between this line and the normal NL or LN. Can I find this angle theta? Yes, I can find this angle theta. Okay, this angle theta would be 40 degrees using your protractor again. The student moves the mirror, okay, to an angle, angle alpha. The new alpha is now 35. EF is not shown on figure 3.1. The student repeats the process with the mirror on EF and places pins P5 and 6. Draw the line passing P5 and P6 until they reach point N. Okay, so I'll join 5 and 6, 5 and 6 until they reach point N. Okay, and then can I measure the new angle theta between this line and LN? Can I measure this new angle theta? Yes, I can measure this. Using your protractor, the line or the angle should be 68 degrees. 68 degrees. A student suggests that when the mirror is moved, the change theta, the change in theta, should be equal to twice the change in alpha. The change in theta should be equal to twice the change in alpha. What was the change in theta? So delta theta, the change in theta, is now 68 minus 40, which is 28 degrees, right? Is this twice the change in alpha? What was the change in alpha? Delta alpha was 35 minus 20, which is 15 degrees. Is this equal, is 28 equal to double alpha? 15 times 2. What is 15 times 2? It's 30. Is 28 equal to 30? They are close. But the question is, are they within the limits of experimental accuracy or not? We need to measure it. We need to calculate it. 30 divided by 28. What's 30 divided by 28? This is 30 divided by 28. This is 1.07. 1.07, meaning that it's 7%. The difference between them is 7%. So the statement, are they equal? Yes, they are equal. Yes, they are equal. Yes, they are equal. Oh, yeah, or you can say that the statement is correct or whatever. Justification, the values are close. The values are close. And you might say that they are within, okay, the limits, within the limits of experimental accuracy, Suggest two precautions that you would take to ensure the accurate results in this type of experiment. Whenever you have a ray trace sheet, you need to use thin lines. Okay, you need to use thin lines. You also need to view the bases of the pins. View the bases of the pins. Question 4. Plan an experiment to compare the rates at which different metals conduct thermal energy. Okay? Different metals conduct what? Conduct thermal energy. This is the experiment. The apparatus available includes what? This different strips of metals. Okay, you have a test tube, a beaker, a supply of cold water, hot water. The shorter section of each strip can fit inside a test tube. The shorter section can fit inside a test tube. The shorter section can fit inside a test tube. So we need to test how good of a conductor this metal is. And then we need to repeat with different metals. You need to repeat with different metals. So how can I do this? First of all, what is the range of values? What is the thing I'm changing? What is the independent variable for this question? The range of values. I'm changing different metals, right? Different metals. I need to state just 5 different metals. You can say iron, steel, copper, okay, aluminum, silver. You have 5 different metals. So this is the range of values, the thing you are changing. And then list any additional apparatuses. Okay, we write down the apparatuses. What about any constants for this question? You need to think about the question first of all. Draw a label diagram. What's happening in this question? You have this this piece of metal, which will start to conduct heat, right? It will start to conduct heat from a hot beaker to a cold test tube. Okay, he said that the shorter section can fit inside the test tube. So this short section can fit inside the test tube. So we will draw the test tube here. This is the test tube, which has cold water. This is the test tube, which has cold water. Okay, cold water. And then we need a thermometer inside it to measure the temperature or the rise in temperature. This is the thermometer inside the cold test tube. What about the longer section? The longer section should be fitted inside a hot beaker, or large beaker with hot water inside it. So this is a beaker. This is a beaker with hot water inside it. And then you need to use a stopwatch. And you need to use a stopwatch. Okay, why do I need to use the stopwatch? To measure the rate at which this hot water would increase its temperature. You have a stopwatch, a very fancy stopwatch. Okay, this is the stopwatch. And you will measure the rate at which the temperature increases, right, of the hot water. That's it. That's all you need to do. So for the so we drew the labeled diagram. You have the shorter section inside the test tube. Okay, you have the shorter section inside the test tube and the longer section inside the beaker. Right? This is the hot water in the beaker and the cold water in the cold water in the test tube. What about you have the range of values. What about the constants? What about the controlled variables? The controlled variables. What constants should we have? We have to have a controlled variable, such as the initial temperature of cold water. Initial temperature of cold water. Initial temperature, okay. Initial temperature of hot water. You need to have same, okay, same volume, okay, same volume of hot water, same volume of cold water, same volume of cold water, same room temperature, same room temperature. We can say, for example, same time taken, and in this case, the final temperature of the cold water would differ. Okay, same time taken. Therefore, the final temperature of the cold water. We don't care about the final temperature of the hot water. This is not an experiment to test the rate of cooling of hot water. This is an experiment to test the rate of heating of cold water. Why? Because you have the conduction, or basically we want to check the conduction of the metals. Same time taken. These are some of the controlled variables. What about the missing apparatuses? Okay, let's check out the apparatuses. Cold water beaker, hot water. So he didn't write down the thermometer. Okay, we need to label the thermometer and the stopwatch. You have to write down the thermometer and the stopwatch. And stopwatch. Okay, so we wrote down some of the missing apparatuses. Okay, and then we need to write down the we wrote down some of the precautions. Maybe we can add some precautions if we'd like. Okay, we might do that. What about the steps taken? How can we conduct this experiment? The steps taken. So add hot water and cold water. Add hot water to the beaker and cold water in the test tube. Okay. Place the metal as shown. As shown. Okay. In the figure. When you place the metal as shown in the figure, leave for a leave for a fixed amount of time. And measure the final temperature of the cold water. Okay, of the cold water. And you can say find the or measure the calculate the rise in the temperature. Calculate rise in temperature by saying V2 T2 minus T1, okay, or delta T or whatever, or delta theta, which is the change in temperature. So this is how you can conduct this experiment. Okay, how can you conduct this experiment? And then you need to repeat for the different metals. Okay, for this question, he doesn't actually need a table. Most of the questions he tells you to write down a table. He does not want this for this experiment. Okay, and then how can I compare them, or how can I write down a conclusion? Do I have any precautions? Yes, one of the precautions is to stir the water gently or take the readings from the thermometer perpendicularly. Okay, precautions, stir the water gently or take the readings. Okay, take the reading from the thermometer. Okay, thermometer perpendicularly to avoid the parallax error. To avoid the parallax error. Okay, so these are some of the precautions. What about the conclusion? What about a conclusion for each metal or for each different metal? Repeat the process or repeat the experiment more than once. More than once and take average. And take average. Then record the readings. Record the readings in a table if you want. I know in this question we do not have a table. In a table, and compare results by drawing a graph or by plotting a graph of what? By plotting a graph of the different types of metal with the rise in temperature. Metals versus the rise in temperature to find the best conductor. Find the best conductor. Okay. Okay.